Hi guys, thanks for joining us today for today's webinar from Today Tomorrow, Evolving HPC with Vast Data and InsightEngine. We're going to go ahead and get started and as folks continue to trickle in. Before we begin, I want to share just a few housekeeping notes with you guys. On the top right, you will see the docs section. This has relevant documents to this session, mostly customer success stories that we'll cover at the end of this session. Please feel free to check those out. I've also linked in there the partner portal. So this is where we will record this session, and you can access these slides and this recording 24 hours post-event. Following this session, we will be sending out the recording, so keep that in mind. Keep an eye on your inbox tomorrow. That's where I'll send the link. Lastly, if you have any questions during the session, please don't hesitate to put those in the Q&A section. You will see the Q&A section over there on the right-hand side. We've posted a screen grab in here just for you guys to view. Your questions will appear once it has been approved. If you'd like to submit your questions anonymously, please do that by checking the hide name box down there on the bottom right of the panel. We truly want this session to be as interactive as possible, so feel free to ask any questions, share your thoughts with our team. And throughout this session, we do have a lot of folks on this call that will be able to kind of field some of those questions for you guys. We are excited to share how VAST simplifies HPC and how InsightEngine is positioned to shape the future. This is going to be a jam-packed session. We have tons of information, great content, great customer success stories with you. So let's go ahead and get started. It's my pleasure to introduce Greg Michon, VAST VP of Worldwide Channels. Greg, over to you.
Awesome. Thank you, Christine. I appreciate it. Good morning, good afternoon, good evening to our VAST partners, wherever you're joining us from. We sincerely appreciate it and are grateful for our partnership with you. Welcome to the VAST Data Solution Series. And by the way, this specific webinar has been moved twice. So thank you for your patience. We had a couple of last minute speaker changes here. We've got a fantastic session set up. And what we're going to be talking today, as Christina mentioned, was VAST Data's high performance computing solution, which was one of VAST's earliest use cases, and candidly, it's one of our most successful globally today. Let me do some quick introductions, and I should move my slide. There we go. So let me do some quick introductions. We've got a couple of speakers and subject matter experts who've joined us today. First of all, I am joined by Andy Pernsteiner. Andy leads our field CTO team globally. He happens to be one of the most entertaining and knowledgeable speakers as well. So we're thrilled to have him. We also are joined by Don Schulte. Don is one of our regional sales directors out of Colorado. He's probably one of our most prolific HPC sales specialists and salespeople in the field here today. Sold many use cases and customers, so we're thrilled to have both of them. So guys, welcome.
Thanks.
All right, perfect. Okay, so we, as I said, we do have some exciting content and some pro tips to be able to share with you throughout the webinar, which you're going to want to hear. We're going to lay out really what we think is the opportunity for our partners. And then Andy's going to discuss kind of the historical, the current, and the future challenges that customers are facing around HPC. We're going to discuss kind of the convergence of HPC and AI-driven workloads and what that really means for customers in terms of unique set of challenges that poses. We're also going to get into kind of our architecture. Many of you are familiar with our disaggregated shared everything, or DAYS architecture, and our software capabilities. We're going to talk a little bit about how those two things are really helping these customers solve those challenges. And then Don's going to come in and really kind of bring this down to a very practical level, how we've been able to leverage our platform and our technology to help our HPC customers solve some really difficult challenges. So please make yourself comfortable. engage with the team as Christina encouraged you to do so. Let's make sure that we have a very active, interactive session through Q&A. All right. So let's talk about your opportunity with VAST selling into the HPC community. And for those partners and those individuals that maybe have not sold into this space, I'm going to just kind of at a really basic level define what high performance computing or HPC is. So in a nutshell, HPC aggregates a ton of computing resources to be able to work in parallel, to be able to calculate on massive data sets at extremely high speeds in order to solve some pretty difficult problems. So in a nutshell, at a 60,000 foot view, that's what HPC is. And HPC can be found in government research laboratories, in government agencies and universities, in industries such as financial services, healthcare, pharmaceuticals, oil and gas, media and entertainment, as well as manufacturing and autonomous driving. Some use cases that we see often and you may end up seeing in the field are things like simulations. That could be things like genomic or fluid dynamics in oil and gas, could be weather simulations or traffic patterns. Another area would be using kind of detailed analytics. That might be seismic processing or high frequency trading, maybe leveraging sensors from autonomous driving vehicles. Finally, an area might be image processing, and some examples of that might be the medical imaging space or biometrics or satellite imagery, as well as movie making. So I want to just kind of break that down for those folks that might not have sold into this space. Those are some common areas where you'll see them and some common use cases and challenges that your customers will face. I think the common denominator in HPC use cases is the fact that they require tremendous amounts of compute power to be able to process and analyze a lot of data. And so that's probably a good segue into this slide here, which is today the world, as according to IDC, produces about 150 zettabytes of data. And some of you have seen versions of this slide before. Structured data, which is that small circle, represents about 8% of the world's data today. And within the context of HPC data sets, this structured data is oftentimes financial data, could be sometimes scientific simulations. As you guys know, structured data will typically fit inside of a database or a data warehouse. It's typically numerical or tabular in its layout. And over the past 30 years, the IT world has been very happy to focus here, building storage, building databases, data warehouses, and platforms to solve and for this kind of data. And for that 8%, the market valuation of companies that are in this space is well over $1 trillion today. And it's growing at about 20% annually. 92% of the world's data, however, is unstructured data. And that's that big circle here. Unstructured data represents the natural world, as our CEO Renan likes to say. It could be things like my voice or imagery or videos or instrument data or genomic sequencing, GPS and sensor data, data that really doesn't easily fit inside of, say, a database or a data warehouse. And over the last 30 years, this data has kind of oftentimes been relegated to archives and siloed storage platforms. We believe that now, thanks to VAST and really thanks to the growth of AI and things like machine learning and supercomputers built on GPUs and DPUs and TPUs, that this data is increasingly being promoted from the data center archives and it's really being activated to train models so that organizations can solve some of those problems and really create amazing value from of it. Unstructured data is growing about 3 times as fast as structured data at about 60% year over year. VAST happens to play in both of these circles, in that entire 150 zettabytes today, and really giving our customers the ability to be able to integrate unstructured data management within a structured data environment, enabling them to be able to capture, catalog, refine, enrich, and really preserve data at exabyte scale. We happen to believe that we are the absolute best solution, bar none, to the challenges your customers are going to face in this space. And so with that, this is probably a good place for us to kind of introduce our first polling question. We're going to have about 4 or 5 polling questions. So Christina, if you would, let's go ahead and introduce the first polling question. For our partners, we'll give you a moment to answer the question, the poll, which probably is going to show up lower left-hand window. So take a moment just to kind of answer those. While we're doing that, this is being recorded for our EMEA and our APAC partners who will replay this tomorrow. And so for our partners out there, unfortunately, you won't be able to participate in this poll. Just wanted to give you a heads up on that. Christina, you tell us when you think we've aggregated and collected.
Yeah, so I want to comment quickly that you'll see the poll section over here on the right-hand side next to chat and docs. So I see a handful of polls coming in right now. Want to make sure you guys are able to access that. So maybe one more second, and then we'll go ahead and share the results.
Perfect.
Okay, Greg, I'm going to put them on the screen.
Excellent. Okay, cool. Let's have a quick look at this. And while we're doing that, Andy, it's probably a good place to bring you in, and maybe does some of the results thus far surprise you?
No, it definitely doesn't surprise me. I think that
it looks like the majority are kind of either they're seeing the merging of HPC and AI either occasionally or fairly frequently.
Yeah, I think we're seeing an uptick for sure. Probably many of you were at Supercompute this past year, and there was definitely a much more of a focus on AI compared to previous years. We see that trending in that direction, increasingly so. What's interesting, I feel like, about the world of AI and the world of HPC is that there aren't so many people coming out of colleges who know how to build out large-scale infrastructure, and well, to do proper model training and all of the large-scale inference operations, you kind of need to know how to build large systems. And so there's a lot of people in the HPC community who have started to embrace AI because those are the people that get turned to when someone needs to build out a farm of 10,000 GPUs or 100,000 GPUs.
Yeah. That's a great point.
Yeah.
Okay, perfect. Andy, I think we'll, at this point, we'll turn it over to you.
Sounds good. So I'm going to share my whole screen because there are some animations that I want to make sure that you get the benefit of. And so I think the first thing that I wanted to do is kind of talk you through a bit about, I guess, our history at VAST in terms of where we've come from and where we're going to, particularly as it relates to HPC communities. And so historically, we've been very focused on HPC. In fact, the first install that I ever did back before we had a product to sell was at the NIH to sit behind their HPC cluster to rip out a GPFS implementation that they had been sort of dealing with for potentially a decade now. And so that was our first install. Actually, my first day at VAST was installing a system at NASA Ames. And so this is where we got our battle scars, you could say, is in the sort of high performance compute grids at some of the top tier research and other academic institutions that we could find. We basically put our systems out there to see who could break it. And that's where we started life out. So I'm going to talk to you a bit about sort of how we see the world of HPC, but then also about how we're solving challenges for customers. And I'm going to go a bit more on the technical side because that's my background. But basically, what we've found is that the implementation that we put together has solved a lot of challenges that maybe people didn't know they had in HPC because they had just been dealing with them for so long. And so what we've built, if this is the first time you're sort of understanding more about VAST, or even if you have a little bit of history with us, it's always useful to understand, like, we've built a platform to basically handle large-scale workloads of any shape and nature. And not only that, but our goal was to always allow for the consolidation of multiple workloads that were unpredictable and high-performance demanding applications. And so, when we started out, we had, basically a lot of, raw performance that came with the system, but the architecture was such to give us all the capabilities that I'm going to lay out for you. And when we first came to market back in 2018, the main focus for us was to basically democratize the deployment of Flash within the data center. And to do that, we had to find a way to make it much more cost effective. And so a lot of the underpinnings of our architecture are focused on making sure that you can deliver all Flash solutions to your customers at a price point that is very competitive, and in fact, sometimes more cost effective than deploying so on straight spinning disk. And so I'm not going to get into the pricing side of things, but I do want you to understand in the back of your mind, everything we've done has been to try to make sure that the customers get the most out of the hardware that they buy. And in fact, we actually don't even sell the hardware. It's up to you to sell the hardware, and we're just putting the software on top, and we're trying to make sure that the customers are able to get the most for their dollar, and it also preserves the most for your margin as well. Okay, let's go through the platform as a whole to make sure that you understand sort of where we're at. And actually, you know what? I just realized I missed a poll. There was a poll on the last slide. Give me 1 second. Let me go back over to it. I apologize for that. So I don't know if Christina, if you dumped the poll out there, or if I have a way of doing it.
Yep, so you guys will see the poll over there on the right-hand side, so you can go ahead and start answering that, and then I will put that on the screen live shortly.
Awesome. And while you guys are answering the poll, I think that in my time here, I've been here about 7 years, which here is kind of like a lifetime. I know that many of you may have had careers longer than that at single companies, but in the course of time, we haven't really strayed from our vision of providing a platform to allow customers to get the most value out of their data. We've just taken our initial implementation and allowed for the expansion of lots of capabilities on top. So nothing that we've done over the last couple of years is any different than how we started off. We've definitely stayed on the same course that we were on. And again, our roots are in the HPC community. So I think you'll find that a lot of the features that we put together and are offering are very well aligned to that. Looks like we're settling in on the poll stats.
Yeah, Andy, and you can kind of see the results over there on the left-hand side of your screen, but I cannot share this poll.
Oh, okay. I can stop sharing if you like, or I can just say what the answers were.
Yeah, that's perfect. Go ahead and share with the audience.
Yeah, it's fine. So it doesn't surprise me either, but there's a kind of an even mix between the voting. The voting here, which is demonstrating ROI or addressing technical complexities or competing with legacy solutions, they're all kind of evenly split. I think that almost nobody said that they were, challenged to educate customers about the benefits of combining HPC and AI. So well, that's good. Like the fact that it's easy or you become familiar with education is definitely good. I think if you would have gone back a couple of years, that probably the poll would come out differently. But getting ROI is, we see it as well, right? The model trainers are out there spending money like there's no tomorrow, but at some point somebody has to make money off of these things. And organizations are all kind of looking at each other to figure out how they're all going to do this. And we're seeing firsthand how people are deriving value out of AI. But I don't think it's as common in the marketplace yet. People are still doing experiments. Okay, so I'm going to keep moving through my slides. The underpinnings of the architecture allow us to offer a platform that has a wide array of services. So I'm going to start on the left-hand side, and then I'll move my way over to the right. And that's actually the evolution of how our platform has evolved as well. The part of the product known as the data store is sort of the foundational layer for storing unstructured data. When they say unstructured, we think about protocols like NFS or S3 that are accessing large scale amounts of data. You could think of it as file data or object data. We actually don't distinguish between the two. Our platform is multi-protocol from an exposure standpoint. So any data that comes in over one protocol can be exposed over another. We've seen a transition from NFS to S3 or POSIX to object over the last several years, and especially more recently as people start to use object storage as a way for doing checkpointing and model training and putting it into more and more of their pipelines. The good news is that customers don't have to change their infrastructure in order to make that transition if they're using VAST. Data that they ingested using a POSIX-based protocol like NFS is immediately accessible over S3, and so they don't have to go and change any of their architecture to be able to support it. In fact, it allows for developers to experiment with new ways of accessing data without having to change the existing patterns so that they can transition as smoothly and seamlessly as they need to. We, being sort of very focused on high performance, also were the first enterprise platform to support GPU direct storage over the NFS protocol. So when I mentioned earlier that my first day on the job was at NASA, we had worked with NASA pretty extensively because they had been doing NFS over RDMA testing back in 2017, 2018. Back before anybody really was looking at it closely, they were running it on their own NFS servers in a sort of production state. And so iterating with them and iterating with several other customers who were on the bleeding edge, we supported NFS over RDMA basically right out of the gate. And our work that we did to support GPU Direct was actually mostly done once we supported RDMA. One key benefit of RDMA is that it doesn't just make it faster, it makes it so it frees up compute cycles on the customer's HPC grid so that not as much compute is necessary to perform I/O, and that actually buys back cores on the customer's compute farm, so that not only can the jobs run faster, but they can do so with less hardware resource. And so again, like it just frees up more resource for customers to do things. Now, GPU Direct is the way that GPU servers are able to access data by bypassing sort of the main memory and going straight to GPU memory, basically from the network interface all the way down to the GPU itself. And so we've partnered with NVIDIA to launch this in a way that application developers can easily take advantage of it. And we're happy to share how that looks with both our customers as well as what we use internally. Now, if I move my way to the right, we've covered the unstructured side of things, and that's where we've made our bread and butter, right? There's many exabytes we've deployed over the last several years of unstructured data storage. But a couple of years ago, we worked with several customers who were deploying us as S3 object store backends to some of their large scale data lakes. And we found that a lot of the time their analytics were running slowly, not because the storage wasn't performing, but because the application was not optimized for reading the types of data that they were reading. And so what we found is that by creating our own database table format, we're able to reduce the runtimes of their queries, as well as, again, giving them back CPU on their compute grids to be able to run more analytics. And so we've created our own database table format that can be used in large-scale data lake or data warehouse applications. And on top of that, we've also created an ingestion pipeline, which includes things like Kafka or direct SDK access to be able to get data in and out of that database easily. And we support the open source modern frameworks like Spark and Trino and Dremio and a few other sort of options that customers want to use. If people are already using Spark in any of their installation, they can take advantage of this database table format and instantly get back a large amount of compute and resource time. And as we keep moving our way to the right, in order for us to get sort of, again, give people the most bang for their buck, we also started embedding our own microservices directly on the platform. So what we call the data engine is basically the ability for applications to run natively directly on the platform. The first implementation of that was a version of Spark that we're launching directly on our nodes, especially for customers that don't want to have to spin up a separate Spark cluster or manage a separate Spark cluster. It's there. We're going to be continuing to extend this. And with some of the software releases we have coming out over the next couple of months, we'll be able to start creating events that then trigger functions that can run directly on the platform as well. So there's going to be a lot more that we'll share with you over the coming months, but there's a lot sort of in store here. Okay, let's talk through a little bit about sort of the challenges that we saw, and I realize that the text on the left-hand side is a little misaligned, but the challenges that we saw when we were looking at how to build a platform originally mostly came from our experience with other scale-out systems. And I myself used to work for what is now known as PowerScale, but back then it was known as Isilon. And Isilon's challenge and many other scale-out shared nothing systems have a challenge, which is that they have a lot of crosstalk, and they also have the need to do things like rebuilds every time there's a failure of some kind on the server nodes. So basically, a shared nothing architecture is one where each server or node has a piece of the data that's going to be requested, which means that if you, for example, are talking to node 1 needs to go consult with node 2, node 3, and node 4 to be able to read and pull the data to send back to you. On the other side, if you're ingesting data to, let's say, node 2 has to talk to all the other nodes in order to acknowledge your write, which means that if there's any slow node in that chain, then the slowest node becomes the weakest link, becomes the bottleneck for your I/O. Because they all have to talk to each other, if one of those nodes goes offline, they have to perform a rebuild because they're not going to be able to pull that information. And so we found that shared nothing systems have limits in terms of their scale and in terms of their challenges when there is a failure. They're also very rigid in how you scale them. So for example, there's a fixed amount of CPU alongside the disk or flash that's in each of those nodes. And if you want more performance, you have to add more capacity. And if you want more capacity, you have to add more CPU. So you're locked into a pattern that makes it more difficult for you to help your customers scale in the direction they need to. So that's a challenge. But what we've decided to do is let's think of a completely different way of architecting a system. And so what we've done is we've created our own way of addressing storage to start with, and then obviously all the services we built on top. And the simplest way to look at it, and we call this the disaggregated shared everything architecture, the simplest way to look at it is that we took the two halves that are associated with storing data and we split them into pieces. There's what we call the logic layer, which is where all the decision making happens. We put that into what we call C nodes, which are basically compute nodes, if you want to think of them that way. And those are the nodes that your clients or your customers' clients will talk directly to. So for example, if you have an HPC grid that needs to mount the file system, they will talk to the C nodes. Those C nodes are able to see and speak to every single NVMe device that's in the lower half of these servers. The lower half, we call them D nodes, D for data, C for compute. So the D nodes are responsible for storing all the state, but they don't make any decisions. All the decision making happens at the C node level, and each of the C nodes is able to see every NVMe device as though it were local, because we're using something known as NVMe over Fabrics to do so. This NVMe over Fabrics fabric can run on either RDMA over Converged Ethernet or on InfiniBand. In fact, we have customers deployed in both patterns, and especially in the world of HPC, there's a lot more familiarity around InfiniBand. We've been working with InfiniBand-based systems for the entire time that we've been in business. So we've found that we've got a very interesting way of approaching it. There is one sort of thing that you kind of have to think about here, which is that we don't necessarily need to add things in a symmetric fashion when customers want to expand. If a customer wants to add more capacity, they can add more D nodes, and they don't necessarily have to add any more compute on top if they don't need more performance. On the flip side, if they find that they have workloads that need more performance, they don't necessarily need to add any capacity to be able to achieve it. And so we found, in large part, that the bottleneck when it comes to all flash media, it's almost never the devices itself. It's almost always the CPU that needs to address it. And so by separating these two components into two separate pieces, we've made it possible for customers to scale them independently and buy only what they need from a hardware standpoint. Again, going back to that whole idea of let's reduce the amount of spend they have to do on the hardware itself, so that that preserves more room for them to do more with software, as well as to provide better margins for partners. So this is sort of the way that we've architected it. And then the other thing to make sure to nail down here is that the D nodes down below, these are highly available fault-tolerant systems that have an active partner for any possible component failure. So think of them more like a disk shelf that has active componentry for everything, rather than thinking of it like anything else. All of the smarts happen up in the C node level in what we call the logic or compute layer. The D nodes, I call them dumb nodes because they don't actually think or do anything. They just receive bytes across the wire and they go onto flash devices. That's it. Now, I want to keep moving through a few things here to kind of give you a sense on, other ways that we see customers deploying. And one of the challenges that people have had, especially a lot of these model trainers now are building out data centers where they have multiple data halls to prevent against a single data hall causing an outage with the rest of their infrastructure. Imagine you're training a large scale foundational model and a bunch of your GPU servers go down because you lose power to one of your feeds. Then you don't want the entire facility going offline. So they separate into these data halls to preserve some ability to segregate things. But then they need access to all of that data and they want to reduce the amount of latency between the accesses. And so that's one example where people are building out multiple vast clusters because they want to have some ability to survive against full power failure to an area. But then they want to share data without having their clients cross-mounting and mounting across sort of a larger network fabric. And so we can easily facilitate this using our global namespace, which means that you can read and write to data as though it were local directly on the cluster that you're mounted to without having to go and traverse anything. We handle the transmission of data when it needs to happen. And some of this is based on prefetching algorithms, and some of this is based on sort of deterministic patterns that emerge as data is accessed. But it's really allowing customers to be able to access data anywhere. And this isn't just for doing within a data hall or in a single data center. In fact, there are customers now who are using this across large wide area networks to allow for external users and entities, including especially in research institutions where they need to have researchers access data in a remote location. Perhaps maybe it's a PI who's working on a project, but they aren't actually physically at the university where they're performing the research. A lot of times they need access to that data, or they might want to share with another organization. So this is an enabling technology to help do that. We have API calls for this global namespace so that you can pre-warm a cluster with data if you know that you're going to be running a large scale job. We see this time and again in the world of GPU training and checkpointing, where they don't want the capacity to be utilized on one of the systems that they're using for GPU training until they need to. But when they want it to run, they want to make sure that GPUs are kept fed very quickly. So they might be pre-warming it using an API call. Over time, we'll start to integrate more with some of the more popular job schedulers, but it's relatively simple from an API standpoint. Okay.
Andy, as we transition into kind of InsightEngine, and you can feel free to go to the next slide. I just wanted to encourage. By the way, I spent about an hour this morning getting a couple people available backstage so that they can answer all your questions. So I do encourage our partners. You guys are usually a pretty loud bunch, and we love that. So please let me encourage you to go ahead and ask any questions, particularly as we kind of get into some of the newer capabilities that we're adding. So with that, sorry about that, Andy. I just wanted to put
all good.
Put a quick plug in there.
I also realized I skipped another poll again. And Christina, if you wanted to hit the poll for the next one, then that way I can give it a moment to run through and I'll announce the results. While people are sort of going and going through and putting in their results, I'll skip back a couple slides to maybe cover a point or two that I might have skimmed over pretty quickly. So by separating the compute and state layers, or the logic and state layers, We've also put we've created a way for obviously scaling independently. We've put in a way to make it so that if there's a server failure, if a CNode fails, almost nobody notices, right? So the way that applications access our system is there are a series of virtual IP addresses that are distributed across all of the CNodes in the cluster. They can be carved up into discrete pools, especially when you have both batch and interactive related workloads. So imagine that you have a large scale HPC job running, but then you have users logging into a login node to be able to do interactive access, like they're trying to go into their directory and look at files. You don't want one thing impacting the other. And so in some cases, what customers will do is they'll segregate some number of those C nodes and dedicate them to specific workloads. And so doing so makes it so that it's easy for customers to run lots of workloads simultaneously without them getting in the way of each other. It's more of like a brute force QoS. We also do have QoS both at the user and at the at the directory level, so that anytime you find that an application is either consuming too much, or if you want to guarantee some minimum viability for applications, you can set those dynamically and they'll take effect immediately. So we're seeing this happen a lot in the world of, again, model training and other HPC checkpointing jobs, where when you have a lot of checkpoint writes coming in, you don't want them interfering with other writes. So sometimes you'll carve off some performance capacity for that. Okay, so the poll results look to be settling in. And, we're kind of evenly split again between people who are very confident, who can articulate the benefits of our day's architecture, and then people who are, know the basics, but they need more support. And, I encourage you to reach out, obviously, to your team. You can ask questions in the Q&A if you have any specific questions. I'm also happy to help work with, work with our teams to make sure you get the enablement that you need to understand, what it is that we offer to customers in a more articulated way. Okay, so let me jump ahead a little bit after that poll was complete. Now I'm going to talk about some new stuff. And I think that we're seeing a lot within the sort of AI space change very rapidly. But one of the things that we see, not as an emerging technology, but now as one that people are deploying in the real world into production use cases, is something known as RAG. Now, I'm not going to explain all the details behind what RAG is, but RAG is effectively a way for you or your customers to augment existing models with their own data. And in many cases, they're doing so in their own data centers so that they don't need to send API calls to OpenAI or to xAI or to Anthropic or any of the sort of large scale model providers. And effectively, the way that it works is the process of doing this involves taking data, whether it's enterprise data, scientific research data, whatever it is, and doing some amount of preparation on it, and creating what are called vectors to go into a vector database. I'll explain this process in a little bit more detail when I get a couple slides later. But in order to get to the point where you can perform inference on it to enable a chatbot or an agent workflow, you need to do some amount of data prep, and there's a little bit of heavy lifting up front. So because of that, what we found is that there's some level of complexity that people have to overcome in order to get to the point where they actually have value to be able to use this within their own infrastructure, or to either use internally to enable their teams to work more effectively, or to use externally to offer services to their customers. There's a lot of pieces in here, but I think what I'll do is I'll show you how customers are deploying on VAST today. And we've had this running in our lab for a bit. We work with some partners also who are able to deliver this as an actual built out service. But effectively, let's imagine that you have a lot of repositories of data. And at VAST, I don't know how it is for the places that you work. We have a lot of places that we put things. We have Google Drive, we have OneDrive, we have Confluence, we have SharePoint. We have all of these different silos, you could say, of information. And for a regular person to go find that information is getting harder and harder over time. So we knew we had to solve this in some way. And so what we've done in our own sort of dog food exercise internally is we take all of this data and we push it into a VAST platform. and we put it onto the VAST data store. And in our current GA shipping release, we support what are known as bucket notifications, which allow for anytime a new file is ingested into a bucket, it will automatically create a message that is sent to a Kafka topic. We chose Kafka initially because it's spoken widely in a lot of enterprise and other deployments, but it's not that difficult for us to also iterate on this and create notification that can go to other places as well. There's a lot of alignment between the way that we develop some of our technology and the way that AWS has developed their S3 implementation, because we need to be compatible with a lot of applications. And so in addition to this, we have a way for customers to access that information outside of Kafka as well. Now, whenever you're doing anything in terms of document indexing or creating a RAG system, you need to make sure you're not wasting CPU cycles or GPU cycles on duplicate documents, right? If you have a bunch of documents that might have proliferated and people made copies of them and put them into your enterprise archive, you don't want to go and index them multiple times. So the first thing that we do is we make sure to hash those with a basic MD5 checksum effectively to figure out, have we seen this one before? And then after we get through that, assuming that it is not a duplicate, we need to extract chunks from these documents. In this case, we're creating PDFs as part of this pipeline, and then those chunks of text are used to be able to go to the next phase. But I'll explain a little bit for a second, which is, in the world of model training, typically you think about things in terms of tokens, right? A token and a word are about the same thing, right? So if you have a 1,000-word document, it's between 1,000 and 1,200 tokens or so. In the world of RAG, you don't think about it in terms of tokens, though. You think about it in terms of larger chunks, because you need context. A word isn't good enough on its own if you're trying to satisfy somebody's searches or questions. It's better to have a sentence full of data. So we're basically breaking data into sentences, and then it allows for customers to then run filters on that afterwards to be able to filter out any PII data, especially in clinical or in healthcare environments, or toxicity filters in cases where you're going to be pushing this out to some external facing community. All of that data needs to go somewhere. And so all of this data is stored in a vast database table. It's not a separate database system. It's within the vast database itself, where we basically store all the text chunks as well as lookup identifiers so that we can find them later. That's also where the deduplication database goes as well. We'll store it in a vast database table. Now, the next phase in this is, after we have the text chunks that have been filtered, we want to go and generate what are called embeddings. And the simplest way to think about what embeddings are, if you're not familiar, is, let's say you have a sentence, which is a bunch of words. In order for it to be efficiently searched for in a vector database, you need to convert it into numbers. So the embedding process is, for lack of a better term, taking words and turning them into numbers. And this works also for video and audio and other types of things as well. It's all about turning things into numbers that can be efficiently stored and retrieved. Now, once those vector embeddings are stored, in our current case, we're storing this in a vector database known as Milvus, which is an open source framework for storing vector information. We'll talk more about what we're going to be doing in the future, but that's how I'm doing it in our environment today. Now, once you have everything stored, for someone to get value out of it, whether it's a user or whether it's an application like an agent, let's say that they ask a question, right? So when they ask a question, they're sending a prompt. That prompt on its own isn't useful because it's a bunch of words. That prompt also needs to get converted into numbers so that those numbers can be searched in a vector store. And the way that you think about it, or the way that I think about it a lot, is, imagine you have an XY plot and the question that the user asks ends up in a certain spot on the XY plot. In a vector database search implementation, typically what happens is you're searching for what are known as the nearest neighbors. And so you're basically drawing a circle around wherever the user's dot landed on that XY plot. And then you're collecting all of the vectors that were close enough to it. And this is, of course, where you have to do a little bit of fine tuning to find the right blend of things. Once those vectors are found, then what we do is we fetch the chunks from the vast database table that match the vectors that were found in the similarity search. So now we have the user's question and we have the chunks of text. That's still not enough, though, because you imagine if you ask a question, you get back a bunch of random sentences from random documents. That doesn't really solve your problem. You still need a real answer that you can look at and understand. And so what we do then is we pass all of that information. We send both the question or the prompt as well as all of the text chunks over to an LLM. Now, the beauty is you don't actually need that good of an LLM to be able to answer the question at this point, because most of the context, most of the value comes from the documents themselves, from the text chunks themselves. The model is just there to take the information and turn it into something that's coherent. So in this case, we're running on a relatively small model, and you can run this on even like a NVIDIA RTX 3050, like anything with like 8 gigabytes to 16 gigabytes of VRAM will run this model. I could probably use a smaller model if I wanted to. There's no need to run some big fat model to do this. And once you do that, you then have something you can send back to the user. Now, what I explained is actually an oversimplification of this process, but I've found that oftentimes, especially customers who are dipping their toes in the water with AI, they might have read a little bit about how RAG works, or they might be trying to experiment on their own. But I've found that oftentimes if you show this diagram and this pipeline to a customer and explain it step by step, as I just did, almost everybody in the room will learn something. Every time I show people, I will learn. They at least 75% of the room will learn something. So it's definitely something to share with people. But there's a lot of things I glossed over. There's also pieces that I didn't discuss. Like I didn't discuss security. I didn't discuss what happens when documents are deleted. There's a lot of bits and pieces. And so what we're working on now directly with NVIDIA is something that we're calling the InsightEngine, which is going to be released in the early part of this year, which will allow for customers to deploy what are called NIMs, or NVIDIA Inference Microservices, directly on the VAST data platform. Let's talk about how that looks. I'll just build this slide out so it's sort of all in one place. But basically, what we're going to allow customers to do is deploy NIMs directly from NVIDIA's catalog. So if you go to NVIDIA's website and you search for NIM or NIMs, you'll be able to find their catalog of all of their microservices that are available. These are battle-tested inference models, embedding models, and other related items within the pipeline. And they'll be able to be stored directly and run directly on the VAST cluster to interact both with the unstructured data in the data store as well as the more structured data in the data warehouse. And so to be able to sort of encapsulate all of this is our next effort, right? So the slide that I showed you previously with the diagram, that is something that we built in the lab and that we've helped customers to build on their own, but it isn't all self-contained in the platform. The InsightEngine is where we bring everything into the platform. We have full support with NVIDIA to be able to use their microservices, and then we'll be embedding our own vectors directly on the platform as well. So we wouldn't be relying on an external vector database to be able to do it. So it's coming out soon. There's a lot that you're going to get from this. It also has the ability to allow for when security policies are set on the unstructured and structured data, then we can consult those security policies whenever a user issues a prompt to make sure they only get access to data that they would have gotten access to normally, right? So imagine that you have a file system and a bunch of directories, and you have a directory for HR and you have a directory for finance. You don't necessarily want the finance people knowing what everybody's salary is because they want to make it lower. But what you'd have instead would be the ability for access policies to be set on the actual directory structure the way you would normally do if you were deploying a file server. But those are applicable also to the vector embeddings that we'll be storing as well. So it's all part of an automatic way that we can ensure the security is consistent regardless of how people access the data. It's been one of our core tenets the whole time. So this is, it's coming out soon. There's a couple build outs that go along with this, but we're seeing a lot of adoption for RAG applications within our existing customer base where they're kind of building it on their own and we're helping to consult with them. This is for the people who don't want to have to go build it on their own, something where they can have more or less a turnkey solution where applications can run and they can have services available for their user communities or even their external communities without having to go build it themselves. And so we think that there's a lot of sort of pent up demand for this, especially as people sort of dip their toes in the water with AI, right? And so I think that, if you want to encapsulate it in a single sort of thought, just take all of the things that we've built our architecture on and now apply AI to it and allow us to encapsulate that and then push it out as a solution to people. And the way that we're able to deal with this or do this is because we started from the ground up on making it all, an all-flash scale-out platform where performance was of the utmost priority, but so is security, so is efficiency, so are all of the sort of core tenets of VAST. and we're just applying those further upstream to be able to make sure that AI can take advantage of it. And with that, I'm wrapping myself up, but there's one more poll that I'm going to sort of kick off for you.
Andy, great job. To our partner community, just take a couple minutes to put your questions in there. And then what we will do is transition to Don, who's going to talk to you a little bit about some real world customers where we've helped them solve some significant HPC challenges, particularly a couple of them that kind of we're incorporating some of those AI capabilities and workloads that Andy was just speaking to. All right, let's see. We've got about 20 people in. We'll give it just another minute. It looks like predominantly about 72% say that complexity and setup and management are the major customer obstacles with traditional parallel file systems. So Don, probably a good place to bring you in. Does that kind of does that correlate?
Yeah, it does. It does. It exactly does, and that's what we're going to talk about with a few of our use cases here. Are the slides up on the screen? Or they're not yet? They will be in a second.
Yep. We'll ask Christina just put starting with slide 23.
There we go. Yeah. So this is actually very important. Our customer case studies are important because the single biggest arrow, the single biggest feather I have, kind of strategy I have in trying to win HPC customers over is actually utilizing our existing HPC customers as reference accounts. They talk to each other, they form communities. Obviously, we have supercomputing, but we have regional communities as well. And every HPC director in a region knows the other HPC directors in that region, and they talk amongst themselves, especially through the public sector with universities, the federal agencies. They all know each other. And if you do well in one area and one customer, it's going to spill over to others. And that's why these case studies are so important. Let's move along. Let's talk about one that I'm familiar with a little bit. Historically, TAC has been one of the largest centers in the United States, if not the largest. Over the last 20 years, they've certainly developed into what's called the Leadership Class Computing Facility. That's the LCCF program from the NSF. But historically, for 20 years, they've been running Lustre. How do I know this? I sold them one of their very first Lustre support contracts over 20 years ago on the Ranger system. That was one of the first InfiniBand HPC systems out there. And but they've also in production run GPFS, IBM Spectrum Scale. They've run BGFS on a production cluster, and they test literally every storage system that comes to market. You think of any modern system, storage system, and they have had it in their labs testing it. And they did that of course with VAST about 3 years ago, and they liked what they saw. They tested it for resiliency. They tested it for scale. For workloads that they knew they had problems with. There was one called a Collins code from a researcher named Collins. That Lustre would scale to about 300, 350 nodes. And then the MDS of the Lustre systems, the metadata servers in the Lustre system would start to fall apart. So they tested Collins code on VAST that they were testing in the proof of concept, and it ran fine at 350. It ran fine at 500, surpassing what Lustre could do. It ran fine at 1,000. It was starting to linearly scale past 1,000. We went up to 4,000 nodes, and it was handling the workload fine. So we were actually beating Lustre on certain workloads in a linear scaling factor. So we could prove we could scale. We could prove we could perform. But what TAC and every HPC customer out there knew for the last 20 years is that you couldn't have resiliency and you couldn't have simplicity along with scale and performance. So typical enterprise storage systems were great at simplicity and resiliency. Typical HPC systems, parallel file systems, had scale and performance, and they just didn't mesh. And that's what VAST, through its DAYS architecture, was able to supply. And we've proven it on the Stampede 3 cluster that is thousands of nodes. And in testing, we're looking at, with TAC, proving it on Horizon, which will be the single largest open science system in the world.
Wow.
They're no longer thinking about in terms of 5 petabytes of capacity, being able to perform at X number of terabytes per second, but they've expanded their view of how can data be the underlying layer of HPC and AI systems that are coming forward. And one of the biggest things that made it all happen, and I would encourage everybody to go through that link for the case study for TAC that we've provided. And you hear Dan Stanzioni and Tommy talk about not just the pain versus gain equation that we flipped for simplicity, resiliency, scale, and performance, delivering all of it, but we're also making it affordable versus what former storage systems based on spinning disk was. Through our DAYS architecture, through our DRR capabilities, data rate reduction capabilities of similarity, we're delivering a affordability equation that now TAC is saying, we're only going to have 2 types of storage going forward. We're going to have flash, and we're going to have tape for archive. Flash is going to be VAST, and of course tape is for archive.
Wow.
So that's the future of TAC coming up. And when I talked about DRR, they're achieving approximately 2 plus to 1 DRR. So effectively, what they're doing is, purchasing and implementing, say, 100 petabytes of VAST, and they're actually storing 200 petabytes of VAST. So that kind of flips the whole equation of affordability on its head, and that's what TAC is saying.
Don, a quick question on that. Because TAC is part of the University of Texas, and they're so predominant in the HPC community globally, do you see their decision to kind of move towards 2 tiers, one being flash, the other being tape? Will that have kind of a spillover effect into some of these other research universities?
Certainly. As a matter of fact, I wanted to bring up University of Utah next, because TAC is the kind of flagship research center for the National Science Foundation in the United States. More what we see is people like the University of Utah. University of Utah is a longtime VAST customer. They hopped on board early with VAST. But again, they were a Lustre shop, had some GPFS, but mainly Lustre. And even in appliance form of a Lustre implementation, we have certain people that package Lustre as a part of an appliance. They were still finding issues with simplicity and resiliency. And they tested VAST and moved over to VAST as well. And they think of in terms of 3 to 10 petabytes on an HPC cluster. And this is what we're going to find across the board, across the other universities in the United States and beyond. And their comment was, after running VAST for a year, it just works. And they're a great resource. But interestingly, though, Utah, especially they have an HPC group, but they also have an SCI group. The SCI stands for Scientific Computing and Imaging. SCI was actually one of if you go back 20 years, back when AI was still trying to determine if cats were cats versus dogs in images, that was like the big fundamental problem. Can we see a cat in an image versus a dog? Or can we see a stop sign versus a yield sign for autonomous driving? They were doing that type of work 20 and 30 years ago. And SCI now runs all of their research systems on VAST. And this gets back to a little bit one of the poll questions about AI and HPC and how they're merging. Utah, and I can rattle off another 10 universities that I work with, not including TAC and not the big research centers. The predominant source of their funding now is AI-based. So whether it is a private university-funded initiative for AI research, or if it's something like NAIR, which is the National Artificial Intelligence Research Resource Pilot Program, I am seeing multiple millions of dollars go into every university for a new AI system that the HPC group is trying to implement. This actually is a challenge, but it's also, I think, an opportunity for our partners, because we just found just happened this week where a university received $5 million to put in an AI system. They're going to carve out $4 million for compute and fabric, and they're going to carve out maybe $1 million for storage. But guess what? They don't have a data center to put it in because of the GPU complications around power and cooling. They came back and said, to the partner, they said, how can we implement this within the resources that we have, the research infrastructure resources that we have? And that is certainly an opportunity that our partners can insert themselves into an HPC system that is with the new AI funding resources.
Yep.
That didn't happen in Utah, but it did happen at one of the other universities.
Don, do you
And
want yeah, go ahead. So,
yeah, we need to wrap up because we're running out of time. I see that. But real quick, there's NASA and Seneca and a bunch of other implementations. I do want to discuss Seneca just for literally 1 minute. It's an Italian consortium of research centers and universities. It's kind of like if you took all of the western half of the United States and said, we're going to build one center to serve everybody's HPC and AI workloads. And that's exactly what Seneca is. They put in 50 petabytes of VAST. And the most important takeaway from Seneca is that they're not just thinking in HPC terms, they're thinking as a data warehouse or a data lake terms, so that data underpins all of the workloads. And what we're delivering there is multi-protocol access for NFS, objects, SQL, retrieval of data, delivering quality of service initiatives across multi-tenant implementations. The big thing there is data catalog that provides SQL access to metadata information around the data. And of course, DIR drives affordability again in an implementation like this. So what we have is a truly kind of data foundation layer to all of HPC and AI across a multi-consortium kind of cloud native based implementation. I think I condensed about 5 minutes into maybe 1 minute about Seneca, but
I think we have to have a webinar just dedicated to you and talking about some of these incredible projects. It's really exciting what's happening, and appreciate both of you guys kind of joining. I know that we've got many partners that have commitments, so we'll start to wind things down. This is probably our only brag slide, but I'd be remiss not to at least touch upon it. Many of you know, last October, Gartner awarded us a leadership slot in the Unified File and Object Magic Quadrant based on our innovation, our ability to be able to execute, and really the outstanding customer service. We're kind of at the, one of the things that Gartner emphasized in that Magic Quadrant was the need for products that go really beyond traditional storage, highlighting the importance of all kinds of integrated data services. And really, we believe VAST is at the forefront of this shift, and we are redefining the requirements for real-time modern data processing. And so we're very excited about this. It's certainly something that you can leverage in your conversations with your customers. I'm going to go ahead, in the interest of time, we're going to go ahead and wrap up. I want to thank everybody. First of all, let me thank their speakers and the folks backstage addressing some of those questions. Thank you for those few questions that did come in. But thanks for joining the webinar today. Hopefully you gained some insights into kind of how VAST is simplifying HPC workflows as well as AI workflows today, particularly when we're accelerating some of those AI adoptions into HPC use cases. We invite you to connect with our teams. You can always send me an email. If you don't know how to connect to your team, it's just gm@vastdata.com. I will be sure to make sure that we connect you with our account team. My final thought before we end this is it is VAST's end of the year. Our fiscal year 2025 is ending January 31st. So we've got about, 16 days to go. We've got many partners that I saw that are on this call here that are working with us on end of the quarter and end of the year deals. We appreciate in advance your sense of urgency over the next couple of weeks and helping us close out those deals and closing out what is sure to be a record breaking quarter and record breaking year. If there's anything that we can do to kind of help you close out those deals, please reach out or let me know, and we'll make sure that we connect you to the right folks. So with that, thanks again to everybody for joining us. Good selling and happy year-end close. Thanks, everybody. Appreciate it. We'll talk to you next month.